and a long-term collaborator, is one of the major experts in cosmological simulations of galaxy formation, and especially cosmological hydrodynamical simulations. Klaus got his PhD in, I should look at back in 2000, okay, under the supervision of Matthias Bartelmann in Munich. And after that, he moved with a Marie Curie fellowship in Italy, in Padua, right, for a couple of years, and then back to Munich with postdoctoral positions. And then finally, since now about 10 years, he has staff researcher position at the Ludwig Maximilian Universität. As already said, Klaus is a very widely recognized expert in cosmological simulation. He recently got an ERC Advanced grant to build up a group working on simulations of astrophysical plasma, especially in relation with the plasma residing in galaxy clusters. And what he's going to talk about today is about the complex life of galaxy clusters. Please, Klaus.
Let me... Okay, so I assume you can see the screen and the pointer?
Yeah, all good.
Yes.
Good. So, yeah, knowing that it's a little bit close to Christmas Eve, and having this kind of Zoom talks, which are always somewhat difficult because it's not very visible what is happening, I thought I start with a kind of small detour to have at least a little bit unexpected here, and maybe also a little bit more unusual and fun things. So let's start with two slightly off-topic fun facts. So anyone has an idea of what you can see here? So you can still be a small group, so you can throw in ideas. Anyone wants to guess?
On the left, something organic looks like.
Yeah, you are quite good. Okay, that's true. So on the left, that's a thin slice through the human brain. And on the right, that's a hypothetical axion density field at a redshift of roughly 1 million. And now you might ask why I show you that. The point is that in structure formation or in cosmology, you want to classify structures, and both of them are somewhat related to problems or to things which I want to show. So on one thing is that there's a already for a while recognized and a lively discussion on that the structures you see, although they might be completely different origins. So here's a human brain and a cosmological web from cosmological structures. Sorry? Can have very similar properties. So here you can see that these two structures, the cosmological web and the cosmological brain, for example, have very much the same power spectrum if you analyze that. And here that's from different works here, even from people in Italy, so led by Franco Vazza, for example. And the interesting thing is that they are quite different from power spectrum you would expect, for example, from normal turbulence or other physical processes. So the idea behind is that these kind of formation processes are leading to very similar structures in certain aspects. And that is just related to how these different networks are forming. And that brings me, so to speak, also to a kind of side note, which is interesting for what we are doing in cosmology. And just as a reminder, so what you see here on the lower right is a cosmological structure and a randomized cosmological structure on the right, and they have both the same power spectrum. So if you just do the kind of simple analysis with asking what is a power spectrum of a structure, you might get the same answer for something which looks much different. And that, of course, now interferes with how it is forming. So that is just a reminder on that we have to be very careful in how we compare things, and that things can look in certain aspects quite the same, although they are very much different, or they can look very similar just because the processes leading to that on long term have very similar properties in their randomness and in how they are building up. And the second thing was this axion field. So if you look at this axions, that is a hypothetical particle here, which is a very good dark matter candidate. And that would come out with already quite nonlinear here at very high redshift. And if you follow that axion field here, and that is a simulation we performed, you see that at a redshift of 100 or so, you formed what is called axion mini clusters. So what you see here is the formation of these clusters. And if you look at them, then they have even substructures and everything. So they look like cosmological structures, and then we know in the very nonlinear form, but on very small scales. And these kind of clusters would then be, so to speak, what we classically would think on dark matter particles, because these structures might survive even to redshift 0. And to give you an idea, so this largest axion mini cluster here in the simulation, if you ask what is its roughly visualized region, it's roughly the size of the solar system and contains roughly the mass of 2% of Mercury. And the thing is that they form in a very similar ways, and then you have cosmological structures forming. So at very early time, they just grow by collapse and accretion. And then after the matter radiation equality, no new clusters can form, and they start with this kind of merging process, also very similar than in cosmological structures. So they then, so to speak, their mass function starts to decay because smaller structures are merging into larger structures, and you only build up more and more larger clusters, but the smaller ones get less and less. So they have this kind of two-phase formation, very similar to cosmological structures. And in that process, not only the most of this axion will be locked into these mini cluster structures, but also the internal structures start to look very much similar than cosmological halos you find. Namely that they don't have any longer just a power law shape, but they start to have this kind of NFW compatible phase. So you can compare that even to what you see in cosmological structures. So here on the right, you have a plot of the mass of normal halos as galaxies and galaxy clusters from simulation and observations, and their concentration parameter from an NFW fit. And you see here a lot of observational data points and the uncertainties, and you see also some simulations here from our cosmological boxes overlaid. And on the left side, you see at a redshift of 100, these red data points are this mass concentration relation you get from the axion mini clusters. And again, note the mass scales here. So here you are at masses of 10 to the minus 12 or 10 to the minus 10 solar masses. And what I found very striking is you can now bring these two plots on scale. And I just did that by a PowerPoint trick to deform the plot so that all the scales are matching. And if you do so, you can see that also they're spanning this kind of tremendously large range in masses from 10 to the minus 10 up to 10 to the 15 here. If you put just a line connecting these two plots, you see that this slope of this line is nicely compatible with what you see in the individual simulations. So again, it shows that the similar just gravitational collapse here of two very different structures. On one hand, is axions in the very early universe, and on the other hand, dark matter cosmological structures here are leading to very similar structures. So because the underlying accretion and merging mechanism is the same. So I found that kind of very nice to demonstrate that here the same kind of process and leads to the same kind of structures on very, very different scales. Now, also, you will never be able to follow these two things which I showed here, for example, in one simulation, because of course the scales are too different. Of course, the computational challenge is to extend the scales of these simulations to capture more and more dynamical range. And here's just a kind of short introduction on how complicated that is. So let's go back to this normal cosmology, which you're used to. So from the fluctuations you see in the cosmic microwave background, all the structures formed by gravitational collapse, which we observe, like the cosmological structures with the cosmological web, with the galaxy clusters on top. But then you have a lot of structures which are imprinted on smaller and smaller scales. So you reach galaxies, but even in galaxies, you have structures in the disk, and even that is always breaking up in smaller and smaller structures. And computational, you have always at a certain point to where you cannot include all this kind of subgrid physics any longer. So you have to think on proper modeling them, or you build average models over it, and you hope that the description, when you build kind of average models for whatever is below your resolution, is still valid and doesn't influence your larger scales. So one of the challenges is, of course, to computationally extend this range so that you'll be able to include more and more of the structures which are on smaller scales than where you start from your cosmological simulations. And to do so, people over the past decades made use of the increased computational power which is available, and from increasing also algorithmic implementations. So what is here plotted is for something like a 20 years or a little bit more than 20 years time scale, the number of resolution elements used in cosmological simulations. And so every data point here in this plot is one of the simulations which was kind of leading at its time. And I also marked here in the recent time all the simulations you might have heard of, like the different branches of Illustris, Multi-Black Eagle, and our Magneticum simulations, which currently still holds the largest simulation in terms of resolution elements, which was so far performed. And you cannot look only that from the kind of pure computational point in terms of number of resolution elements, but from a more physical point. So what you could look at is the same kind of thing in a plot where you plot on the x-axis the most massive object you have in the simulation. So basically, you might want to reach very massive galaxy clusters in your simulation, but on the other hand, the resolution, so you want to have a lot of resolution. And as you can imagine, in that kind of diagram, so to speak, a diagonal line here is a line of constant effort. And as you can see, all the different simulations, which you might have heard of here, roughly are populating this kind of diagonal line, because you have only a certain, you're limited in the amount of effort you can, computational effort you can put into your simulations. So of course, also here the goal would be, and the goal is from various groups, of course, to expand here, because basically you want to have a lot of resolution so that you can study your galaxies, but you also want to have the proper environment. So you want to have massive objects in there where the effect of the environment is maximum. Now, as you saw in this previous plot, we now reached the level where we have simulations which are holding 10 to the 12 resolution elements, which you can imagine is a huge amount of memory and computational power. And just to give you an idea of what that means, so here's a short record of the power consumption of SuperMOOC when we run this very big simulation. So you see here on the y-axis the computational power, the electric power the computer took. So it goes up to almost a megawatt. And here on the x-axis is the time. And that's only a very small part of the simulation, because these simulations typically run something like weeks on the computing systems. But the interesting thing is that in this power consumption here, you see even some of the important computational steps. So you see global time steps, you see checkpointing, you see whenever something is failing. So basically, you have to be aware of that you burn a lot of electricity when you run these large simulations. Now, how does it look like when you have this kind of very, very large simulations to form? Well, in the first glance, if you just look at the full simulation, and here you can see how the structures evolve with time. And what you can see, of course, the very large scales, it doesn't look very spectacular, because basically what's happening is that all the structures are just condensing out, and all the action and all the interesting dynamics happening all at this kind of collapsed structures here inside. And the appreciation of what you see here in the simulation comes only if you, so to speak, combine all these things and you zoom in on these nonlinear structures, like here's the most massive galaxy cluster. You zoom in out of this large cosmological web, even into very large supercluster region where the galaxy cluster here is on the center. And what you see here is already the gas density. So you see the intergalactic and intercluster medium. And at a certain point, you can even switch to the stellar component in the simulation. You see the BCG and you see all the member galaxies here of this cluster where we're zooming on. And you see that this kind of very large dynamical range even allows you, when you then zoom into the central region of the cluster and you see the BCG, you see even structures still in the BCG. And if you look very carefully, you see that there are different colors here, which are reflecting different ages of the stellar component. So it shows you how this BCG formed and gives you also a kind of dynamical remnant of how the structures formed. So basically, that is kind of the state of the art you can now reach nowadays with these very large simulations. And of course, the question is how you can do cosmology with that. And as you might know, counting galaxy cluster is a very powerful tool in cosmology. And I showed you already before that it's very difficult to distinguish structures, and it's quite hard. So here's something from a very old work, which is, but it's very nice illustrative. So when you compare, for example, a universe with a cosmological constant compared to a universe without a cosmological constant, which is tuned to form the same structures at redshift 0, you can see how in the past the different structures here have different galaxy clusters. And I, so to speak, connected that to this mass function here you can see. So that is the growth of the number of objects at a certain mass over time. And again, just to give you a kind of marker here, so a mark where, for example, a very prominent galaxy cluster in the local universe like Coma would be. However, nowadays the goal of cosmology, or the goal of inferring cosmology, has pretty much changed from this kind of early days where these plots are coming from, where you were interested, is there a cosmological constant or not, up to a day where we really have to look in very detailed aspects of your cosmological background model. And here I just, for again making this point very clear, I show you here some, again, already kind of outdated simulations, where on the left side you have 5 different simulations of cosmological models, which different versions of dark energy in terms of quintessence model or cosmological constant. And all these models which you see here are already ruled out by observations. So the range of allowed models is much smaller than shown here, but still you can see that it's very difficult to see differences here in the structure. So if you want to measure cosmology with the structures, you have to do it in a very detailed way, and you need very accurate predictions to really improve our current understanding on cosmology. And another example I brought here is on the right. So here you see the influence on things like early universe physics, like giving imprints in a non-Gaussianity of the initial density fields. And as you can see here, the non-Gaussianity parameter you have here in the simulation is already a factor 100 larger than what latest measurements from the CMB still allows. And again, you see that even with these large factors, the cosmological structures are looking very, very similar. So the point is that nowadays, if you want to do cosmology, you have to understand the formation of the structures in very, very detail, and you have to also understand all underlying physical processes. Which brings me to the point to ask, now we're doing this kind of very large simulations, including baryonic physics. So how good are our simple or are our predictions? So we can even start with the most simple predictions we have, namely the properties of galaxy clusters as a whole. So not going even into any kind of small details, but just looking at galaxy clusters as a whole. So that is a plot you saw already before when I introduced this NFW and the mass concentration. And again, what you can see here is halo mass versus the measured concentration. And what you can see immediately is that individual simulations, like here's this cloud of data points that are several hundred thousands of clusters in one simulation, have already intrinsically a very large spread. Now in the simulation, we understand the spread because we can classify these galaxy clusters as very relaxed or dynamically active systems, and we color-coded here the objects according to that. And you can see here this kind of very clear segregation, such as kind of more dynamically active clusters here have a much lower concentration as the very, very relaxed ones. Now in observations, you have interestingly a very similar scatter, but here it's of course much more difficult to understand how much is coming from your observations, because you see that the error bars here and the observations are already quite large, and how much is coming from this dynamical state. However, you can see in some of the observations that you see the trends that this very relaxed structures have also much higher concentrations than the unrelaxed ones, similar to the observation, similar to the simulations. However, you see all these different lines inside here, and that are all predictions from different simulations. And there you can see that even the individual simulations have still slightly different predictions for the same kind of quantity. And that is also not only because of a little bit unknown in the baryonic physics beyond, but also that it's very difficult to have these simulations over a very large dynamical range to make this kind of mass concentration relation a little bit more meaningful. And you can see here that these different clouds you see here are different simulations at different resolutions, which are combined. So they give you then a kind of very long leverage range, but that also would mean that here on the left, the simulation have many orders of magnitude higher resolutions than the one on the right. So you have to be very careful on if all your baryon physical processes are converged inside. Now, speaking about this baryon physics inside the clusters and inside the simulation, you can look at a couple of quantities and compare that to observations. So what the example see here is prediction of the amount of gas, so intercluster medium within galaxy cluster as function of its mass. And again, you see a lot of data points here and overplotted again with different simulations. And again, here I stacked our simulations here at different resolutions and different box sizes, so that again, you get a very large dynamic range. And in this log plot, all that thing looks quite nice and convincing, and you can say, okay, that's a very simple thing, so it works out nicely. However, if you look in detail and go away from this log plot, but just look at the linear gas fraction, where you just normalize the amount of gas you have in the object to the cosmological fraction you had in the simulation, and compare that to data points, you can see here that the different simulations on the market here are really predicting very much different amount of gas you have even in these very massive systems of groups up to clusters. And that is one of the still inherent shortcomings, that our description of how the feedback processes inside the structures are working is still not good enough, or it still varies among all the simulations in a significant manner, so that is not a very firm prediction here of the simulations. And the reason is all these different simulations are typically calibrated in different ways. And many of the simulations are typically calibrated on stellar properties here at small halos. And you can immediately see that when you have your description of the physical processes which are important for galaxy formation, and you tune them to reproduce some galaxy properties you would like to have, it's not guaranteed that then you get even the simplest thing for galaxy clusters correct. And you can not only look in the gas properties, which of course is always a nice thing, but you can alternatively look into this baryon conversion efficiency, and that is just the amount of stars you form normalized by the amount of gas you would have in a certain halo if the halo would have cosmic baryon fraction. And again, you see the same simulations you had before, and you can see that also here the predictions are very much different, and the gray bands are some interpretation of observations. So you can see also that it's not so simple to interpret the observations, what should be the correct answer. But again, you see that the different simulations here vary by huge amount. So basically, at that point, we are still limited by our understanding on how to implement galaxy formation physics in these kind of simulations. Now you can ask, in general, what is the impact of having baryons at all in these simulations? And what you can look at is, for example, the ratio of the power spectrum in the hydrodynamic simulation compared to running the same simulation with just dark matter, because that is the easiest thing, and most models are just based on pure dark matter simulation and calibrated against that. So that is a kind of very interesting question. And again, you see that if you look at the different simulations, they have again kind of very different predictions for that. But interesting enough is that the prediction here for the power spectrum, if you compare that with the prediction of the baryon fraction in galaxy cluster, is linked. So it's a little bit positive news, because although the different simulation here give different signals, you very fastly understand why they are giving that, and you know how you would need to calibrate simulations. So as soon as the simulations would reproduce the observed gas fraction in galaxy cluster, the different signals here in the power spectrum would be very similar. So that is actually a very good news, and again, emphasize why understanding of galaxy clusters in simulations and reproducing their properties is very, very important if you want to use simulations as a cosmological probe at all. Now, all that, of course, links to all the astrophysics, which is going into galaxy cluster formation. So I'm going now even a step back and just ask the question, how complex is the life of a galaxy cluster? So how complex is its formation process? And what I show now for you is a movie of a galaxy cluster, and that is one of the highest resolution simulations we currently have at hand. So the galaxy cluster at the end is resolved by 10⁹ particles within the virial radius. And if we ask for substructures, we can find up to 100,000 of galaxies inside. And what you see here color-coded is the intercluster medium, and this kind of flickering thing is the shock finder, which is indicating where shocks are. So at the moment you see the accretion shock in the outer parts with this white flickering things, which are very strong shocks, but now you see already inside the cluster medium shocks appearing, and they collide with the accretion shock, and now already the internal shocks have moved the accretion shock much further out. And you can see that this kind of merging of the structure and the growth of this galaxy cluster is permanently steering the intercluster medium, shocking it, bringing a lot of non-thermal motion inside. It's heating up the medium to the virial temperature. And you can immediately understand that it's, of course, very difficult to take these kind of complex objects as a kind of single object where you infer a mass in a hydrostatic equilibrium or so. And again, you see that this merger, which is now infalling, is creating a lot of shock waves which are interacting. You saw even colliding shock waves inside, and now you're driving the third wave out to the real radius. So it gives you an impression on the complexity of the formation of these objects. Okay, so as I said, the interesting point you see in the simulation, and that is something which was in principle known already since quite a while, but on the other hand, never demonstrated such clearly in the past, is that when you now look at, for example, the appearance of shocks in the intercluster medium, and that is the histogram here on the left, where the color code is the time. So red is very early time in the cluster, and blue to black is very late time in the cluster. You can see this kind of two phases of formation of the galaxy cluster. So at the early time, you just have the accretion shock, and these are shocks which are typically have very large Mach numbers because they correspond to very cold material which is falling onto the cluster and gets then realized in this accretion shock. But with time, that amount of gas which is heated by that way is going down, and you have more and more internal shocks. And these internal shocks have typically Mach numbers of order of 2, 3, 4 or something like that. And they are basically in charge of heating the intercluster medium. And if you now look at these structures, you can see here on the right, you see the cluster at a certain time, and you see the real radius here as a white circle. So that is what you would classically think it's the real radius of the cluster. And you can see that here the shocks already propagated further out. You have all the cold streams of the filaments which are penetrating the hot atmosphere and get only shock much further in. So the shocks most of the time propagate quite fast into this more empty regions between the filaments. And so there are 3 directions here given in this plot, and you can see here in the lower panel how the real radius grows here of the cluster and how the distance to the shock is growing. And you can see that with time and with all these internal shocks which are pushing further and further, this accretion shock of the cluster is sitting further and further out. So for the gas, this simple idea that you have a real radius, and at the real radius you have the real shock from the accreting material is not longer true, because all the internal shocks are pushing out the realized region in the gas, which makes all the theoretical models, of course, much more complicated. The question is, can you already observe that or see that? And the interesting thing is, indeed, there are now very detailed observations. So here on the upper left, you see an X-ray image of the Perseus cluster. And what they found here is that they found a contact discontinuity, so no shock, but a contact discontinuity at very large distance. So they had measured that to be almost 2 megaparsec from the center. And it's very difficult to explain why you would have a contact discontinuity in the hot medium there. So the simplest textbook explanation for contact discontinuities in clusters is, of course, what is called sloshing. So you have a more dense inner material, which is, so to speak, not at rest, but it moves within the cluster potential. And therefore, in the direction of motion, you get always a contact discontinuity. But to get a contact discontinuity at that distance would imply timescales which would be many, many gigayears, so almost 8 gigayears, which is still smaller than the age of the universe, but very difficult to realize. The interesting thing here is, if you have this colliding shocks, as you see in the simulations, and you can make here a very simple model for that, then this collision of the shock with the accretion shock would not only push the accretion shock forward, but even leaves a contact discontinuity behind it, and even a refraction wave further in. And now you can make a very simple model where you try to make a simple 1D model for that. And what you find is that you can very nicely reproduce the observations of this contact discontinuity here at the correct distance by these colliding shocks within a relatively short time. So the time scale between this merger-driven shock and the state where you get this contact discontinuity on the correct point is roughly 2 gigayears, which is much better and much more in line with what you observe. And the interesting thing is that you get even this refraction feature here a little bit further in, which could in principle correspond to what is observed even further in. So this kind of simple processes here, on one hand, can very nicely explain some very complex observations, which otherwise are difficult to understand, but again tells you that the intercluster medium is much more complex and difficult to interpret. So the question, of course, arises, how precisely can we measure then masses if this intercluster medium is such complex? And the interesting thing for galaxy clusters is that out of the total matter budget here in galaxy clusters, of course, you have the galaxies, which by themselves are only a very small amount of the cosmic baryons which are available, but you have also the hot gas here, as we are discussing, and you have various different observations. So you can take the X-ray observations and assume hydrostatic equilibrium. You can look at the shadows the cluster makes against the cosmic microwave background, the so-called Sanyaya-Soldovich effect, which gives you another measure of the independent measure of the pressure. You can use the dynamics of the galaxies, and you can use gravitational lensing. And here's an example for a galaxy cluster where people combined all these different methods and compared them to each other. And you can see here that the reconstructed mass as function of the distance here very nicely compares between the different methods. And here I added even the data point from Planck, which measured this shadow against the CMB. So all that thing is quite compatible for that cluster. But again, it's a log scale and uncertainties are still large. So it's still questionable how good you can do that for cosmology and for large cluster samples. And another thing in this respect is that, of course, although in general, we think we understand how to reconstruct masses and they are in general compatible, we have to make some assumptions on hydrostatic equilibrium and additional pressure terms. And there was one very nice recent observation, and that is something which already was also shown already a little bit before, but not in this kind of systematic way, where people looked at basically the non-thermal contribution as function of radius as shown here, and that is basically something which is telling you what is the amount of turbulent velocity, or what is the contribution of the turbulent velocity to your energy budget. And the interesting thing is that here independent simulations, this orange and the green line, are just at the upper edge of the inferred distribution you observe. And you see that here are many observations here inside, which are this blue band and the pink band, which means that on one hand, if you have a galaxy cluster which is dynamically very active, it is compatible with the observations, but you are completely lacking galaxy clusters which are from its internal structure and internal turbulence as relaxed as it appears in the observations. So apparently the simulations seems to not reproduce this kind of very relaxed systems with where the turbulence is already decayed and then put away. And of course, that brings it to all these extra physics processes you might have to include. So you have to ask very detailed question on what viscosity is doing in the intercluster medium, on transport and equilibration processes within the cluster medium. And then, of course, that gets even more related issues like what are cosmic rays doing, how can internal shocks accelerating cosmic rays, how does transport processes work in the intercluster medium. And then you realize immediately that all of that depends, for example, of things like the magnetic field, which is yet another unknown player here in the field. And all these complex physical processes here is of course very difficult to handle, and it would be a kind of lecture by itself on what people can do and do at the moment. But apparently all handling of cosmic rays and viscosity and magnetic fields is very much in an early stage. So no one knows exactly how to handle these things. So that is a very large search field. So as that gets very much complex, people are looking for other possibilities to constrain to go to our goal to constrain cosmologies. So we can look at extreme structures. So maybe they can help us to to understand if we can learn something on our background model from observations and simulations. So one interesting candidate here was the observation of one of the Hubble frontier cluster here, about 2744, where, as you can see, that is a very dynamically active system with some observed shocks. But the interesting thing is it has a lot of substructures here measured by weak lensing. And if you just take all the substructures you measure here in the weak lensing and compare that with simulations and with the intrinsic outcome of simulations, there is the claim, and there was a large discussion in literature, that these substructures are much too massive compared to what you naively infer from simulations. However, it was only compared to dark matter simulations and only, so to speak, compared in a very rough way. So to check if you can really learn something from these objects, you have to do a much more careful discussion. But that is interesting because in principle, if you cannot reproduce these objects in simulations, that's of course something which is very interesting for your cosmological background model and understanding a little bit more how valid that is. So we had a student, or we have a student, which started to look at that. So he again took one of our large simulation boxes so that we have very massive objects. He selected 29 of the most massive systems in this simulation, and just performed in principle the analogous to the observational steps. So first you find the objects, you can center them on the galaxy distribution, so forget about all what your simulation is telling you in terms of where the deepest potential is and things like that. Just do it like you would observe it. So you take the stellar component, like here the galaxies, you center on them, you can identify then all the substructures. You can build a background model by taking the rest. You can do like the observers, you build the cylindrical masses here inside the substructure. And what you find is that if you do it in exactly this way, like the observers have to do because they observe it projected on the sky, the cluster is not longer such an outlier. So you can see here as function, here's the mass of the substructure in terms of the system mass as function of this many different substructures you have. You can see here the red data points are the observed one, and the light blue points here are the identified in the simulation. So you can see it's a huge gap, so there's no way to get these masses. But if you do this procedure that you sum up the masses in the cylinder as the observers do, you find this kind of very massive structures. And you can do that even in various different projections. And you can see that, of course, we showed here one projection which was very optimal already, but there are many of these projections here. So the conclusion of that experiment is that this cluster is very extreme because it's among the most massive clusters in our very large simulations, but it's unfortunately not unlike. And so unfortunately, we cannot learn anything on cosmology of these objects, except that it again tells us that when we want to learn something on cosmology and compare simulation with observations, we have to do it in a very careful way because these are very complex systems, so you have always to do it in a very very detailed way. But maybe it can help to go to higher redshift and look there for extreme objects and see if you can learn something from that. So again, there was recently, already now 3 years ago, a very nice observation of a very massive, what they call core of a cluster, basically a protocluster at redshift 4.3. The interesting thing is that these clusters, when you look at the dynamics of the member galaxies, is already realized and has a mass of more than 10 to the 13 solar masses at that redshift. This is very extreme. It has 14 confirmed member galaxies. And again, they compared that cluster, they found two observational models, and they couldn't manage to reproduce that. So again, we can look in more detail in hydrodynamic simulation. And again, that is an experiment we did. But first here again, what was their argument is, so for example, if you look at the star formation rate in this cluster, and what you can measure is the amount of star formation you have within a certain area on sky. And the black line here is this protocluster we discussed, which is marked here. And there are a couple of other protoclusters, which are meanwhile observed here in this other lines. And the two bands here are the best prediction of simulations. So you can see there's no simulation which comes even close to having this kind of very large concentrated star formation in protoclusters at that redshift. And on the right side, you see the cluster mass as function of the redshift. And again, you see how much outlier that cluster mass is compared to, for example, the Millennium simulations. So again, we took our large cosmological box. We selected protoclusters at that redshift. And from the 16 clusters, which were potential protoclusters, we made a list of the 8 best ones, and among them, they were the one which have the most star forming rate and the most galaxies and the largest real mass. And among that was also the one which had the most massive BCG at that time. And here on the right side, you see our eight candidates. And the interesting thing is some of these clusters had already galaxies which were quenched, which was something on surprise on our side, that simulations at least start to have quenched galaxies at that high redshift in these environments. Now, if you look at one of the best candidates here in a little bit more detail, you see that the member galaxies here have very highly rotating, very thick galaxy bodies. So already there you have some kind of classical, not classical, but very turbulent disk galaxies forming in that environment, which interesting is very similar to what is observed. So here on the right side, you again see the observed protocluster, and on the left side here you see the region at the same size here extracted from the simulation. And you see here the rotational map of one of the members we have in our simulation. You see a rotational map of one of the brightest galaxies here, and you can see that both are indicating that we have very highly rotating gas disk in the member galaxies. So did we found thing because it has same amount of substructure, it fulfills the realization criterion, it has even very similar member galaxies? Not yet, because even if we plot then this total star formation rate here as function of the area of sky, we see that this observed protocluster here by far outtakes all the candidates we have, even the best ones which I showed you before. So again, we didn't find this total star formation rate. However, what we could now do with the simulation, as it is a full hydrodynamic simulation, we could look at how much gas is there. And here came a surprise for us. So if we then do the same plot with the amount of gas and not the star formation rate, you can see that here our protoclusters are nicely reproducing what is observed. So the interesting thing is that in these protoclusters, there's enough cold gas as in the observations. So we have even some clusters which have slightly more cold gas than in the observations, but that is not forming stars. So that points just to the fact that, as I already mentioned before, we have huge uncertainties in how we model our galaxy formation process, how we model star formation and cooling. And that is clearly showing that at this high redshift, our simple models, which are typically calibrated at redshift 0, does not work. But we have enough gas, so in principle, we have this protocluster. It's just our description of the baryon physics, which makes that looking different. So again, unfortunately, also these extreme objects are not a good hint for learning something on cosmology, but again, we learn something on baryon physics. And we can look at even a little bit in more detail. So you can look at how many protocluster masses we get compared to this plot as before. And the interesting thing is that these 8 protoclusters we selected, if we trace them back in time, it turns out that they are not among the 10 most massive clusters any longer at redshift 0. Which again shows you that this kind of simple mapping, which we typically have in mind, that we think that when we see these very massive structures at high redshifts, that as the progenitors of the most massive system today, that is not necessarily true. Because we have a very complex way of how structures form. And the reason why that is so different can be seen here. So what is shown here is the Lagrangian region of all the particles at redshift of 4, which finally end in the real radius, which is the gray radius here. But the real radius at redshift 4 is this red circle very much inside here. So basically what you see at redshift 4 is only the core which is forming of a very large structure, and the total mass of this final structure is much more defined by its environment and not so much by this core. And I see Stefano is unmuting, so I assume I'm running out of time. I don't have a problem. Yeah, sorry.
No, you still have a few minutes, Klaus.
No, I'm almost done. Because, so to speak, I assume that here we have the head of the Coma fan club in the audience, Andrea, but unfortunately he's not here. But that was the slide for him. So we have also simulations where we have constrained initial conditions. So we have simulations which try to reproduce a local universe. And in these simulations, we have, for example, clusters like a Coma cluster. So we can look how the Coma cluster, which is one of the most prominent structures in the local universe, look at a redshift of protocluster phase. And apparently, although it's one of the most massive clusters in today's universe, at redshift 2.7, it's only among the rank almost 200 in the masses. So it's very small. So again, that's very nice to show with the simulations on how different the information paths of these objects can be, and that has to be a little bit more careful in interpretation. So as time is going up, what should you have taken with you? So I hope I could at least show you a little bit how challenging simulations are in terms of computation and in terms of physics, which you have to put in, and that we really stress modern computer systems up to the limit to do these things. And that galaxy clusters are very complex. Still, they are proof of cosmology, but you have to understand a lot of the internal physics of galaxy cluster to do the correct interpretation. So I leave you with the take-home messages here for more discussion and questions.
Thank you very much, Klaus. Thank you very much indeed for this comprehensive presentation of simulation cosmic structure formation with a focus on clusters. Questions from the people in the audience?
Yeah, maybe let me just say, you can either ask your question by voice, or you can type your question in the chat. Yeah. And as well as for those who are on YouTube, you can type your question in the YouTube chat. Thanks.
I see Elena raising her hand, and then Tiago. Elena, please.
So I have a question. When you show the stellar mass function comparing different simulation, so there were two of the curves that were from Magneticum. So one was from the box 2 and the other from 4. So the shape was a bit different. So I was wondering if this was due only to the particle resolution that is different, or also the baryonic subgrid physics is also different between the two boxes?
No, the baryonic subgrid physics is supposed to be the same. But as in practice, much of the subgrid physics is formulated in a way that it's not necessarily resolution independent. You can have very large differences in different resolutions just because your formulation of the subgrid physics is not resolution independent. So you can try to calibrate that away, and that's some groups are doing that, and I think that's fine. That's you have to scope with that. But for the Magneticum simulation, that was not done. It was really try to run the simulation with the same settings at that time.
Okay, thanks. And then, well, a short comment on the hydrostatic mass bias. So I understood your point that you are focusing mostly on the fact that in simulation we don't reproduce the turbulence cascade, and so we cannot have a system that are completely relaxed. But to be fair, and we have also to add that there are observational evidence that there is a bias, or we expected that there is a bias in the hydrostatic mass. I am referring to the sigma 8 discussion
Yes.
for the Planck results.
No, that's absolutely. The only comment is that when you do that, you have to be aware of that you start to have a lot of details which you should take care of, or sometimes you cannot even, remember your work where you tried even to include the turbulent term and in the hydrostatic deconstruction and things like that. So I just wanted to make the point that it's a very complex system, and it's questionable how far we can come if it really then goes towards very precise measurements.
Okay, thanks.
Jago?
Hi, Klaus. Thank you for the very nice talk. When you were discussing basically the non-thermal energy and driven by mergers, this kind of thing, do the baryonic physics really matter on when you have massive clusters merging on, and then you have all these shocks coming basically from the merging, right? So I imagine that even adiabatic runs would present those shocks, or am I missing something?
Yeah, well, the simulation I showed you was a pure adiabatic one, just to show that effect. However, if you have then cooling and star formation, you have to keep in mind that the structure of the atmospheres, even on the early clusters, is changing. So it makes some difference in the details of how shocks are injected if you have a cool core cluster merging into a cluster, or if you have just a non-cool core cluster merging. So at that point, it makes a difference. It makes no difference for the fact that the galaxy cluster atmosphere will be visualized by the internal shocks, and there will be these merging shocks. But then details on the shocks will depend on that. And there's this classic example, for example, for the bullet cluster, which people for a while couldn't reproduce, even in idealized simulations, the bullet cluster. And that was just because you really have to set up an infalling structure which corresponds to a cool core cluster to drive that shock and to get that separation. If you just do non-radiative cluster mergers, you're not able to reproduce the bullet cluster, for example, just because the structure of the atmospheres don't allow you to get this kind of configuration if you not start with cool core systems.
Okay, thanks, Klaus. If I may, just another technical one. You showed this evolution of, the simulation effort as a function of both size and resolution. What is the technical wall? For instance, if you want to increase by 10 each one of the cases with the technology that we have today?
Well, the technical wall, for example, is different here. So technical wall in the lower right thing is that you have a full box and you need larger machines. And unfortunately, currently the memory, for example, is so expensive that if you look at the full computing system, so now we have already the next generation compared to the simulation where we run our very large box, but the next generation of computer has not more memory, or only a factor 1.2 or 1.3 more memory. So actually, we couldn't run a larger simulation even on the next generation of computers because they didn't grow in total memory size enough. On the upper left part, you are completely dominated by latency and imbalances and technical walls, because you can imagine you have a simulation with many hundreds of millions of particles, and you want to run that on 100,000 of cores, but you have always, so to speak, a handful of particles on the smallest time step, which is of course very unbalanced because you have 10 particles and you want to run it on 100 million cores or so.
So I guess we have to think to
different areas of that diagram.
Yeah, I guess we have to think to a new parallelization paradigm with respect to what we have now, and also to probably a different criterion and organizing the time steps. Maybe we should get asynchronous at some point or something like that. Are there curiosities from people not in the field after being shocked by our meta language like baryonic physics?
Maybe I have one, given that you ask explicitly for people not from this field.
Absolutely.
I work in condensed matter theory and simulation, so really a very different topic. But we also have to deal pretty much with the HPC and the challenges. So I was wondering, at some point at the very beginning of your talk, you mentioned like the power consumption of the simulation. And it was not clear to me. Do you have a dedicated cluster to run the simulations, or you exploit, say the facilities, national facilities like?
No. That's run on a national facility, and it was a key project. So we got the full national facility as a monolithic block for 2 weeks to run the simulation.
Okay. So you got the full class, let's say the full supercomputer for okay.
Yep.
No, in itself, the code that we are using scales up very well up to a few tens of thousands of cores. I mean, it depends on the configuration, the dynamic range that you intend to cover. Yep. But in the most balanced configuration, there are no major issues in occupying a whole tier 0 machine. Problem is the power consumption. I think this is a point where we have to discuss a little bit more in the future, Klaus.
Yes, and just because if you might be interested, you see the spiky behavior here, for example.
Yeah.
And that is causing even huge problems at the computational center. Because what is happening here is, if the whole machine is changing its workload on that small base, you get, if you're not careful, you get small variation in the voltages at the processors. And all the modern architectures have even detectors for power outage, which are switching off things. So for example, when these things, and that's not only affecting our codes, that is basically all codes which run on full tier 0 systems, they typically have to bring the system in a very defined way. So they have to switch on all the backup batteries and things like that, because otherwise, in the first peak of the voltage, controllers are switching automatically off, and you get in an awful state of the machine. So we had a lot of this kind of technical problems you don't think in advance when running these things monolithically on a tier 0.
And if I understood correctly what you wrote in the slide, you're also saying that basically, given that you're using so many nodes, on average, they die during the simulation. So so the failure happens during a single simulation, which is something I never thought of.
Yeah. So if you take the full machine, I think I don't remember what was the longest continuous time we got, but I think it was once we managed to get something like 9 or 10 hours in one thing without having interruption. But most of the time, we set even the the T-start point writing here to 3 hours.
So, but basically, your code is capable of keep on running. Either some of the resources are failing during the simulations, because
so we write every 3 hours. We wrote every 1.5 hours we wrote a restart file.
Okay.
Whenever the machine died, we at most lost 1.5 hours.
So it's not a single run. It's okay. There are restarts. Okay. Thanks a lot for.
But of course, as we are moving toward exascale and many more computing units, this is getting more and more a problem. And at some point, the failure must be handled by, I don't know, by middleware, I guess, because otherwise they will become very frequent. I see Andrea maybe wants to add something.
Yeah, I have a very naive question triggered by one of the first slides with the brain. I don't know if you can come back. So.
Almost there.
year or so. It's very naive, but just to understand better. So when one establish these analogies and for power spectrum similarity, can do this, to what extent this can be used to have effective models for the brain? So, because since these similarities are in certain cases deep, so can be used to construct or propose effective models for the brain itself, or not really, in the sense
no,
that...
not really. So the discussion goes more in the direction that the fractional nature of both networks is very similar, and that both networks are driven by a lot of random processes which accumulate up to the effect, so that they then end at the same level of complexity.
But do this can be used to propose a effective model for the brain itself, or not really?
No, not really. I think it's more kind of reminders that you can have this kind of physical processes which have very similar underlying processes, so to speak, which are accumulated up and lead to very similar things. But if you look, for example, at two-point correlation functions, you will see that these two structures are very much different.
Okay, so without the knowledge of a microscopic interaction among neurons, let's say, one cannot really dig more. Okay, thank you very much.
Other questions or curiosities to ask Klaus? Because if not, I don't know whether Antimo want to conclude today's session.
No, I just wanted to confirm that there are also no questions on YouTube on the chat, so I think we're good. No, I just want to thank a lot Klaus Dolag for joining us. It really apologies. So okay, let me turn on my video as well. Apologies for having to give asking you to deliver a talk a couple of days before Christmas. So,
Santa Claus.
Yeah, it's a little bit you gave us, it's a gift for us, right before Christmas to have your talk. So thanks a lot for
You're welcome.
being available, and also thanks a lot for actually following our prescription. This series of talks is really targeting everyone at the physics department, so not just specialists. Ideally, also students. So today we didn't have so many, but in general, when we don't do seminars before Christmas, there are quite a few of them, and they really, I think, benefit a lot from insightful research talks, but that give a sufficient background to allow everyone to follow and take on something. So thanks a lot.
Let me just add that usually before the lockdown, Klaus used to visit us at least once a year or maybe twice a year. So as soon as this crazy period will be over, we have good chances to have him in person next time, maybe.
No, that would be great. Just last thing, we will resume with our series of seminar, this Colloquium series. The next one will probably at the end of January, but I'm still waiting for the confirmation by the speaker, about the exact date and if he's really available or not. So we will meet in 2022. And so for now, just happy holidays to everyone. Thanks a lot for joining, and see you in a month.
Bye, everybody. Ciao, Klaus. Thank you.
Ciao.
Bye-bye. Thank you.
Bye.
Thank you.